definite article, the, from my title relative to the program. There really should be some, I think, mathematics. There'll be a lot more, and some of that was already conveyed in the first two talks of the morning. And you will notice a strong overlap of themes between my talk and Jack's, which is actually not a coincidence, because for the last 4 years, Jack has organized an international body to look at the software challenge of exascale, and I think I've been to 5 or 6 of those meetings, and taken a lot of cues from the computer architects and system software people at those meetings, and tried to look at how that will change the world that I think the majority of us in this room inhabit. But although the themes are all the same, I hope the focus is complementary. There's more than enough material for a day's worth of talks on exascale challenges. So this is the roadmap document. If you just go to exascale.org, you can find the entire proceedings, breakout sessions, white papers, a lot of discussion to get into some of the details. I would say that the mathematical aspects of exascale have been underrepresented in those 8 meetings so far, and there's a lot of opportunity, especially if you're young and you're going to be spending the next 25 years to speed up in this new world of exascale. So extrapolating exponentials is unwise, as Jack noted, and we really are at a crossroads, I believe. The steady progress from giga to peta to giga to tera to peta at regular 1,000-fold improvement every decade using the same single program multiple data, bulk synchronous communicating sequential processes, whatever your favorite computer science acronym is, and roughly the same class of algorithms. We've been improving them within the bulk synchronous framework. But EXA is qualitatively different. It'll be much harder. And the other interesting feature is that what EXA requires is already relevant at much smaller scales, including the strong scaling that will occur within your own laptop, as within a reasonable fixed budget of memory, we get an order of magnitude more cores. And in fact, going from peta to EXA is the same as taking your laptop from 1 core to 1,000 cores. The million-fold nodes will stay the same. The weak scaling up to 1 million will stay the same, but the strong scaling within a fixed memory budget, a fixed memory bandwidth budget, more focus on locality, more focus on heterogeneous architectures, that can be explored independent of your budget to acquire high-performance computers, really, and rethink algorithms with reduction of communication and data motion. So I think that core numerical analysis and core computational science or scientific computing will have to confront this paradigm shift to maintain sponsor relevance. Those will be the machines that we will be expected to make efficient use of. And I would say this is not a distraction from our main work. I would say this is a great intellectual stimulus to try to redo algorithms from 25 years where flops were expensive and data motion could be neglected to just the reverse. And obviously, not everybody has to do this. There are many mathematically fruitful directions that are architecture independent. That's obvious. But the news is that there are now so many more that will be stimulated by architectural constraints. So I believe that modelers, chemists, physicists, biologists, material scientists, and mathematicians are on the front line, because without new models and without new mathematics, the architectural passage to exascale may yield little additional fruit. And the other good news is that mathematical scientists will find the computational power to do the kinds of things that we've been promising, such as the post-forward problem world of uncertainty quantification, of control, of optimization, of inverse problems, of data assimilation, the kind of things that run big loops around the forward solve will be accessible, and also multiphysics, complex systems. And mathematical scientists will participate in a very exciting integration of the third paradigm of large-scale simulation and the fourth paradigm of large-scale data sets. Digital data is doubling every year. The number of scientists is not doubling every year. The mixture of two ugly parents, simulation and observation to create beautiful children, is an important one that mathematicians and statisticians will be very involved in. Think of an exascale computer as a 10 to 100 petabyte data repository where you can access a lot of the data in parallel and use it to improve simulations. And finally, remember that exascale at the lab means petascale on the desk or in the departmental cluster. Now, I don't have much by way of reviewing the architectural challenges because we had Jack's preface. I would just point out that in between his table, which showed that by 2020 we have 10 picojoules per double precision fused floating point multiply add, and 2,000 picojoules, namely factor of 200, to fetch one of those operands from memory. That's a huge gulf of a factor of 200 rather. But there's even a factor of 10 between fetching another operand and moving it 2 centimeters from one end of the chip to the other. So the big news is not that optics might save us going to remote chips, but that the copper on a chip is going to be about 10 times more energy expensive than the improved semiconductor devices. And in other words, Moore's law does not end. Moore's law sort of says you can get for every factor of kappa in increased doping, you can get kappa squared more devices per constant power, and so that much more per unit area. That still works, but the transmission doesn't work anymore. I mean, the transmission has never worked, but it was always the small term, and now it's the big term. The more devices per square centimeter doesn't help with scaling the power loss on those linear distances between devices on a chip. And so now the transmission costs overcome the computation costs, even apart from network considerations. So this is why I say, it's a laptop problem as much as a DOE lab problem. So I think I may have a slide from that roadmap of swim lanes that Jack showed that I'll skip, but I'll just summarize things here. There are many potentially exciting paths beyond this sort of negative news about CMOS etch logic with copper vias, but not within a scale in a decade. And there are many ideas for new programming languages, programming models, domain-specific models, other than beyond MPI plus X, where X is something like CUDA or OpenACC or OpenMP. But they won't penetrate the main CS&E workforce within the decade because the codes that we want to run, such as the one we just heard before mine and the one we'll hear after, they are MPI-based codes. We have billions of dollars of such software in Europe, US, Japan, China. We are not going to be able to agree on something other than MPI plus X. Even agreeing on X is going to be interesting. Of course, MPI has to be made more robust. That's taken for granted. Many things will evolve under the label MPI. So I don't think I have to show this slide because Jack talked through it in delightful detail earlier. But there is this constraint of getting 1,000 times more arithmetic with only about 100 times more memory, and maybe only 100 times more memory bandwidth, maybe less. So while everything increases exponentially, not all exponentials are equal. And so storage capacity and bandwidth diverge below the concurrency of many core heterogeneous processing capacity. Mean time between hardware interrupts shorten, and billions of dollars of scientific software hang in the balance. I think I'll mostly skip the 3 main architectural hurdles other than to flash their headlines. We all know that because the power scales roughly as the square or cube of the frequency, we can't get there by speeding up the devices. We have to have more of them. We know that if we fix a power budget and say memory gets half of it, then there'll be a certain restriction of bytes per second to flops per second, which is very unfavorable. Think of a double precision floating point multiply add that uses 3 inputs and 1 output. That's 32 bytes, and we're getting fractions of a byte per flop. So it's more than an order of magnitude of deficiency of feeding those processors if all the operands have to come from somewhere other than registers or high-level cache. And these are some miracle diagrams showing the best hopes for the memory industry to push that intersection of, let's say, 20 megawatts to the right with different costs of memory and their speed. And a similar kind of thing if you fix the acquisition cost for the memory system at half of the $200 million. Here are some state-of-the-art and miraculous improvements in memory that say we'll for an exaflop system we might have at best 100 petabytes of memory, probably much less. So operating on the edge like this with power and with acquisition, the voltage difference between 0 and 1 will be reduced. Circuit elements will be smaller, subject to more random noise, subject to more errors that must be caught and corrected. Power will be cycled on and off dynamically by the runtime system or something hopefully below the programmer's level in order to keep the chips from melting or just make them less power consumptive when they're not being used. I think that if we had the ability to weak scale, we could go well beyond 1 million. I mean, there are, back of the envelope complexity estimates showing how many processors you can use per problem size with a fixed assumption of the topology of the network and the ratio of arithmetic to local communication. I'll do that back of the envelope thing momentarily, but weak scaling is actually not hard if you can afford the memory per node and if the performance of those nodes is reliable enough to budget your time between synchronizations. The real challenge will be expanding the number of cores per node up to 1,000, and this has to be done with a much smaller budget for memory bandwidth. So it's basically an emphasis on strong scaling, and as noted, it's already about a factor of 10 to the third slower to retrieve an operand from deep memory or off the board than to perform an arithmetic operation, and this could get worse. So all operands really must either be shipped thousands of cycles ahead of time and be available from registers or upper cache. So the missing mathematics here is almost identical to Jack's list. We need greater arithmetic intensity in our algorithms, more flops per bytes moved. We need reduced communication, reduced synchronization, and assured accuracy with adaptively less floating point precision. And that last one, of course, portends some very exciting new emphasis on numerical analysis. We've been just pushing stability under the rug with default double precision for a long time with great success and focusing on other things, but now we're back to the 50s, right? 50s and 60s. This will lead to quantifying trades between limited resources within a fixed error budget. And then in addition to all these things, just to maintain our infrastructure, there's all these new exciting things like uncertainty quantification, data assimilation, inverse problems, and so forth. I think that even on the poster session outside, the roofline model of arithmetic intensity is shown. I probably don't have to say much about it here, except it's always worth pointing out how poorly sparse matrix vector multiply does compared to algorithms that can, like SPMV, inside, say, a multi-grid or Krylov loop, solve a Poisson equation. I mean, so can n-body solvers, and they are 2 orders of magnitude better in the reuse of cached or registered resident operands than that sparse matrix vector multiply if you assume that the matrix has to be reloaded. The line on the left up until a fixed capacity of floating point precision is reached shows the relative use, if you will, of the memory bandwidth as the processor, as the algorithm becomes more flop intensive. And ultimately you saturate with the processing efficiency, but that's a long way away from where we mostly live down here in the very sad part of arithmetic intensity space now. There are, of course, this is a classic emphasis. It was important before, and there are classic techniques that get you a constant in this direction, like S-step Krylov methods. If you can afford the extra wide halos, you can reduce the number of communication steps. There are block Krylov methods which improve the convergence rate by lifting the small eigenvalue. We just heard about tall skinny QR, which reduces the number of communications from the number of columns down to just the log of the number of processors, the optimal communication lower bound. Very exciting, directions, but after all, we're only talking about, constant here in the end. There are also things that occur at finer scales, less synchronous fine-grained messages just to do a distributed map vector if your matrix is distributed by rows. MPI is a little clumsy, but there are sub-MPI communications, for instance, in the new Blue Gene Q, the SPI, which show actually very nice, but again, constant, order 10 or so improvements in the ability to do sparse networks by splitting the on-chip and off-chip work. Another domain of synchronization reduction is one that actually is a byproduct of an an algorithm that I know Rolf cares a lot about, which is the nonlinear Schwartz, which says instead of a global linearization, a global Jacobian of perhaps billions of rows, sparse rows, and a linear method like a trilog method accelerated by multigrid, which synchronizes many times within a Newton step, you could actually have local domains of synchronization by having local Newton problems within that billion unknown system. This was originally proposed for nonlinear robustness ideas when everyone was still doing single program multiple data, bulk synchronous, and in fact it was considered a big deficit of this algorithm that you didn't have good load balance synchronization. Different Newtons in different domains take different amounts of time. It's a nonlinear problem, and then you're waiting for them all to get to the master global Newton. That was a bad thing, but maybe in the new architectures that will be a very good thing. So we shouldn't expect to escape causal dependencies. I mean, the new algorithms will still have to satisfy, for instance, the properties of the elliptic Green's function if you really want every source point to influence every field point in the answer. But we should really ask fundamental questions for science of interest. Do we really need the answer everywhere? Maybe we need some functional of the answer, which is actually easier to attain. Or maybe there's an entirely different formulation that can produce the same scientific observable in less time and energy. So let's see how my favorite method is so vulnerable to this change in paradigms. Iterative methods based on domain decomposition and message passing, a very versatile algorithm for unstructured grids with complex inhomogeneous physics and so forth. The computation and the near-neighbor communication are both fully parallelized, and Amdahl's law is defeated in the realm of weak scaling because the communication is lower dimensional in the computation, surface to volume. And as long as you can load balance well, this algorithm should weak scale forever. But in fact, and this is easy to illustrate with a simple model of the on-chip computation, the near-neighbor communication, the global synchronization, which is a function of network diameter, and then on a per iteration step, you can do a simple estimate, like here, let's neglect the near-neighbor communication because it's usually smaller than the synchronization cost. And it's a trivial thing to show that the number of processors can scale linearly in the problem size in weak scaling if you have the memory to go with them. And this, of course, however, assumes perfect synchronization. And I have to admit that even the log of a billion begins to become large after a while. But this is very good weak scaling. If instead of a hypercube for the logarithm you have a torus, as was discussed earlier, with p to the 1/3 cost, you can only scale to the 3/4 power of the problem size. But still, the weak scaling is not the issue. And familiar with this kind of an algorithm, there are steps where you do local communication to complete the off-processor stencils, a local purely parallel row proportion Jacobian vector multiply, a preconditioner sweep, which is again without communication, some inner product at the end of the B inverse A preconditioned trilog step, and some update of the state vectors per node. And that master iteration, if you can make sure the communication is well balanced and the computation is well balanced, does weak scale very well. But we could, at a billion cores, if one of them is holding up the rest, not for an algorithmic or load balance problem, but because of a hardware issue, like unreliable arithmetic or power cycling that slows one down, it's clear that this should not be an outer kind of a loop, as we often use it for today. And Jack already outlined, in fact, this is actually a common project through our shared research scientist Hakan Altayev at KAUST. One example of breaking the bulk synchronous paradigm, which synchronizes not only at the loop level, which is a convenient way to write code, artifactually building a lot of ordering into what could be a much more concurrent process mathematically, but also at the subroutine level. We say do this task, then do this task, then do this task. So we have two granularities of artifactual synchronization relative to this picture that I think might be exactly the same one we showed, which shows how the three phases of solving a generalized eigensolver can be interlaced in terms of data dependencies through the use of directed acyclic graphs. And this is a thing that, I think this is an area where the dense linear algebra world is now leading the sparse after maybe 20 years where it was felt the algorithmic creativity was on the other side, and we have to all pay attention to this and see where sparsity can enter. Another thing that's endangered is the whole sales job that exascale will be good for multiphysics. You can now do oceans, you can now do atmosphere, you can now do ice. Now you can do them all, in one computer. But the way we write codes, we do those steps sequentially with some kind of a outer loop operator splitting. Here's an example from a fluid structure problem, which you would think of as an atmosphere-ocean problem, where maybe the models are on different time scales, but they have to synchronize at the slower time scale for some flux interface, or if this were rad hydro for some volume to volume bulk surface, bulk source term problem. And we assume that we can load balance the steps and pass an amount of data which may be proportional to the amount that's computed from one subroutine to the other. And if data passing is 10 times more expensive than, or even copying from one set of coordinates or discretization to the other, if that's 10 times more expensive than the computation, then we have our model completely backwards. And I think even these complex physics codes will be rewritten to use close coupling at the physics level, what affects what, and not at the conceptual level of how do I solve one PDE and then the other PDE. And this is not just multiphysics that's the problem. This is all the good stuff. I mean, if you think about uncertainty quantification, one of these models is the state variables and the other one is the PDFs. We have a lot of codes or a lot of conceptualized problems where, say, the states and the Lagrange multipliers or the states and the optimization variables are segregated like this. And I think that this all has to be reconsidered with the realistic memory models in mind. This is co-design, at the algorithmic to algorithm level, not the software to hardware level, which is also required. So just as you would not today in a atmosphere-ocean ice model allocate different portions of the machine to each because there's too much data motion, you would do this. You would sort of make each of them data parallel at the same granularity, but this assumes you can load balance them, and what will really happen, I believe, is that there will be sort of some dynamic work stealing that maybe preserves as much locality as possible, but makes up for the very different arithmetic performance of the different nodes due to randomness that comes from the hardware. So I now have 5 slides of bad news, good news, from the point of view of the problems of rewriting scientific software. We will undoubtedly have to control data motion more than we do now because it carries a high energy cost. And if you want to write an efficient code, you have to pay attention to what costs. But on the other hand, we'll finally get the tools, the actual programming hooks and the performance monitors to control the vertical data motion. We've gotten used to controlling the horizontal data motion with NPI. We've gotten used to segregating from heterogeneous processors. Jeff mentioned the FPS 164. Now they're called GPUs. But we paid this price before, gotten rewarded for it, and we will pay it again, and in finer grain detail, hopefully through some very good software that spares the greatest pain. But we will want to control things like prefetching and locality and so forth within the shared memory context, the NUMA context. Optimal formulations and algorithms like multigrid and FMM and other things, well actually FMM is extremely well proportioned for the new hardware resources, but some algorithms are not. They were designed for a different universe, a universe that is no longer relevant to us, mostly, of expensive flops and flat memory. So we may be forced or lured into more interesting formulations like Lattice-Boltzmann instead of PDEs. The hardware non-uniformity will likely force abandonment of BSP at the outer levels, or maybe outer and inner. And a hardware algorithm non-uniformity will then be indistinguishable at the performance level. So a lot of careful work that has been done for adaptive algorithms to dynamically redistribute the load Or it may be inhomogeneous physics, like an atmosphere model when the sun is shining. There's a lot more photochemistry with stiff integrators than on the night side of the Earth. Those kind of algorithmic non-uniformities will perhaps be able to be swept into the amount of work that we need to do rebalancing dynamically with the hardware. They sort of look the same when you come to a synchronization point. So maybe those tools will sort of complement each other. We're used to uniform high precision. This is wasteful of storage and bandwidth. Just think of the task of tabulating a function on a mesh of 1 billion points. If it is a smooth function, there's a hierarchical basis that represents that function in many fewer bits, right, relative to some implicit hierarchical basis functions rather than just the nodal ones. And we will have to learn to compute and communicate deltas between such states rather than the full state quantities, just as was done back in the 50s and 60s when precision was expensive. Maybe we'll communicate efficiently too. Of course, we'll do data compression on the fly because flops are cheap and messages should be small, but we may even have memory built into the communication hardware that says the last time this domain communicated with this, these bits were all the same, I'm only passing you the ones that are different. And we'll have to address the very difficult task of error propagation and equidistributing error to reach some guarantee within an optimizing resource use. Fully deterministic algorithms may come to be regarded as too synchronization vulnerable. And rather than wait for data, we may use machine learning or statistics to infer data. And then when the data actually does come, maybe we'll have to, rewind a bit. But maybe, it's in a high Fourier mode that's going to be damped anyway. So there'll be a lot of, perhaps user-based resilience in making up for missed messages or error. In fact, we may even type data when we declare it to, how important it is that its integrity be preserved. If it's a memory address, you have to stop everything and get it right. If it's a pixel in a movie, you probably don't care. If it's an unknown in a diffusive model, maybe you can bound the maximum error that could make in space and time and decide, hey, I don't stop the calculation to get that one right. So this is throwing a huge burden of resilience into the user space. That will make it very interesting. But certainly reproducibility, as Jack noted, is something that we can't expect high-performance users to care about. So I do believe programming models will still be message passing with a more resilient form of MPI. Load balanced blocks scheduled today with nested loop structures will be separated into critical and non-critical parts. And the critical parts will be scheduled with DAGs, and the non-critical parts will be made available for work stealing, just like we might write an operating system. So I'll give an example. The example comes a slide later, but to take advantage of such asynchronous algorithms, we need greater expressivity in the way we code. We need to create separate threads for logically separate tasks whose priority is a function of algorithmic state, and join the priority threads, order them as Jack pointed out in the DAG, and fill idleness with non-critical work. And there are some steps in this direction. How would that work for my favorite, sparse Newton-Krylov kind of thing, where the critical path is solving a linear system, bounding a step, and doing a state vector update. We do many other things within that set of loops that could be, skipped or given a lower priority. We recompute the Jacobian where we could, reuse an old block. We refresh the preconditioner. We test convergence at a rigidly scheduled, set of locations causing a synchronization. We do algorithmic parameter adaptation. We do I/O, compression, visualization, data mining of our ongoing simulation. These are examples of tasks that could fill, spots on the critical path where the primary state vector update may be time dependent or iterative loop is stalled. There are many sources of non-uniformity in, say, the hardware, the already important ones that we know about. Ever tried to debug the communication performance or the parallel efficiency of a code where the translation look-aside buffer was an order of magnitude more of a problem on one processor than any others. There's already a lot of variations when you come down to winning a Gordon Bell Prize, but there'll be new ones. Power management, more soft errors, more component failures, and the cost of mediating resiliency will be an unpredictable algorithmic or cost that may go into the system software. Now, of course, there's a lot of non-uniformity for the best algorithms, the ones that don't win the Gordon Bell Prize, but because they're not so uniform, but they're very efficient. And the effects of both types are similar when it comes to weighting and synchronization points. Programming practice. Prior to possessing exascale hardware in 2018 to 2022, we can prepare by exploiting new programming paradigms on many core and heterogeneous nodes. I notice from the posters doing that aggressively here. I call that exascale work. It should be funded under that label. Attention to locality and reuse is valuable at all scales, including today's extreme petascale. And if we can, reduce domains of coherence and make them hierarchical, it's a win-win on petascale systems already. New algorithms and data structures can be explored under the assumption that flops are cheap, almost free, and moving data is expensive. And a key thing is that you have a lot of hardware on the computer, not just the processor, and independent tasks have complementary demands on those resources. Maybe they can be interleaved in time. Paths for scaling up applications. Weak scale to the limits of distributed memory, proportional to the number of nodes containing extra memory. Strong scale applications beyond this, proportional to the cores within a node. Scale the workflow, proportional to the number of instances that can be done pseudo-independently in a MapReduce kind of way, for instance, in statistical ensembles. Can these three things be multiplied together, factor of 10 from each, to get from peta to exa? Very likely. That's easier than making one of them do all the work. And hopefully, that's really true. And then the co-design process can be staged with each of these kinds of strategies. This is a list of some of the software that usually doesn't come with an extreme scale system sold to you by the vendor, except maybe for the compiler. Right? This is the kind of software that has to be written by grad students and curated at say, the national labs by some junior staff scientists. It's very hard to build a career that way, but we know that if we want to do astrophysics or nuclear fusion or global climate or computational combustion, that we have to do these things. And I have my own tiny little world that is rather extremely vulnerable to peta to exa. Hopefully people in this room and elsewhere are working on all of those other categories that are related to the model, that are related to the code development at extreme scale, and that are related to actually a production use of the code, the workflow controllers, frameworks, data mining, and so forth. This is a snapshot of, I guess, 8 or 9 applications that are running at KAUST right now. On the computational science side, we try to have a SPEEDUP philosophy from the USDOE, the Scientific Discovery Through Advanced Computing program, which said, you have to use a common base of math and CS people. The physicist no longer writes their algebraic multigrid solver or their visualization routine, but there's sort of a forced co-investment in a small community. This isn't ideal. This is only something to be approached, but it is an ideal to be kept in mind considering the billions of dollars of software that have to be moved. So I don't know how I'm doing on time. I think I have some time for questions, but if we have a less than decade goal to get to exascale, then we could compare that to a less than decade goal that seemed quite impossible when it was first announced by Kennedy in 1962 in a speech at Rice University announcing the Moon program, saying we choose to do these things not because they are easy, but because they are hard. That's why it's worth doing, because they are hard, and because that will spawn a whole bunch of other great benefits, from global positioning systems to freeze-dried orange juice, right? I mean, think of all the things the space program gave us, even if we didn't get to the moon. And that same thing applies here. We need low-power devices for cell phones. there's a migration of technology in which exascale fits very well. That goal will serve to organize and measure the best of our energies and skills and so forth. Jack noted that we have a 20-watt device between our ears, and that will have to take us to the exascale. It's a sort of a peta-ops device, not flops, as we know from doing arithmetic. But it's a pretty good device for maybe rethinking the algorithms. And it doesn't take up a basketball court of racks either. So it's not only very power efficient, it's very space efficient somehow. And I guess I would point out the existence of a sort of a review article on the algorithmic side of the exascale initiative that came out in the January 2011 issue of Compte Rendu, the why and how exaflops. It's written from an algorithmic point of view, and it sort of gives us some references relative to this talk. And I thought I would unveil, for the sake of SPEEDUP, a new logo of a center that I expect to start in January when my term as dean sort of graciously expires. And so you may be familiar with the Coast logo over here, and so we have a sort of a SPEEDUP version of that for you to commemorate the 41st version of the SPEEDUP conference. So that's the whole part. Okay.